Here we go on exponentials day 2. Today we're going to connect it to some application stuff. So we have exponential growth, exponential decay. First we'll talk about the growth side. So when you have exponential growth, remember that this part, this stuff in here, is going to be a number that's going to be bigger than 1, right? Okay, and in this case we're going to be given growth as percentages. So I'd like to just talk about how you calculate percentages of stuff real quick. So we'll just go back in time. I'm going to add a scratch paper page in here, and let's just talk about like a scenario where you have a percentage. Let's say we'll use my daughter's like allowance for an example. Okay, so Nova she gets like $5 a week. That's hopefully she's not watching this video because she doesn't actually get $5 a week. She gets like 3, and then I never pay her actually. So. But anyway, so $5 a week, and let's just say Nova did an awesome job. She actually did. She mowed the lawn last night. Okay, she didn't empty the bag once. So when I got out there this morning, and the bag was so full, I don't even know how she was pushing the mower around the yard. But let's say I gave her a 20% raise because she did such a good. She went above and beyond her chores. So how could I calculate that? If I gave her 20% more, how could I do that? Times what, Dylan?
Oh, you set it up so you have 100% and then have 120 of 5 by the 100 and then you multiply.
Okay, so Natalie said you times by 0.2. Okay, so if you times it by 0.2, I'd like to start there. That's going to give me 20% of $5, right? Which would be what? You guys got to be good with percentages. Come on, they're not that bad. Let's go. What's 10% of $5? 50 cents. You move the decimal 1 over. Okay, so 50 cents, and then now if you know 10%, you double it to get 20, so it's going to be $1. So now this is going to be $1, and so now $1 is going to be the amount that I give her extra, right? So now to total up her new allowance with this bonus, I'm going to have to do what? I'm going to have to take $5 plus the $1, and I get $6. Okay, that's the long way to do it. Yeah, there's a better way to do this, and I'm wondering if you guys have learned this along the way in all the math that you've learned. How can I calculate 20% more? I can do this in one calculation. Kaylee. Okay, percent over 100 equals part. That is a true statement. But that's not really, yeah, that's going to complicate things. That's true, because we're not, yeah, that's not going to get us anywhere right now, but that's not true. Good double negative there. Okay, any other thoughts? How can I get to $6 without having to do 2 operations? I don't want to multiply and add, I just want to multiply. Is there something I can multiply by to make it equal $6? 80% of that would be if you were taking away 20%. Yeah, so that's the next slide actually. Haha, 1.2, good job. So if I can do this, and this is the thing with percentages. If you want to add 20% to something, like when you're calculating tax, I would do this if I was calculating tax by hand. I've done this several times. You're going to take the amount that you have and multiply it by 1 point, whatever the tax is or whatever you're taking. So if I multiply it by 1.2, that will get me straight to my $6, and I only had to multiply by one thing, right? Okay, so that is why when we go back to the page that we were just on, we are going to, for growth, we're going to take 1 plus the rate, and that is going to be the growth factor in our equation, in our function. All right, so terms here, A is the original amount of whatever you have, T is the time frame, it could be years, days, weeks, minutes, seconds, whatever, and then the rate is going to be your growth rate as a decimal. Let's do an example. The original value of a painting is $9,000 and the value increases by 7% each year. So let's write a function specific to that exponential growth. So we'll say the f of t is equal to, the original amount was 9,000 times 1 plus the rate. So if it's increasing by 7%, I want to multiply that by 1.07. And that will add 7% to 9,000. Yep. And then I take that to the t power because this is like a formula. Question? So now, yeah, so now the question says, all right, there's my, this is like my formula, right? And now it's going to say, hey, I want to know what the value is after 15 years. So I take 15 and I substitute that in for t. So I have f of 15 is equal to 9,000 times 1.07 to the 15th power. Now, last hour, I kind of got a little crusty attitude about with students about them not really doing the best job they could. And one thing that I think you should be doing is when you're sitting in class here, you should be practicing on your calculators. So you should be taking in your calculator 9,000 parenthesis, and then you type all this in. Make sure you know how to use the calculator that you're going to be using on the assessments. So I mean, it's like practice. So we're at practice here. I get $24,831.28. That's money. Dollar bill. Wow, it's a lot of money. Just think if you had 9,000 and it made 7% interest each year, and you let it roll for 15 years, you're going to have 24,000 bucks. That's why everyone always talks about investing money when you're really young, and then the compound interest just goes off the chain. Yep. It goes off the chain, and if you just don't touch it and you add to it, when you get to be older, even older than me, you're going to have a ton of money. Yeah, we get Nova going around the neighborhood, selling stuff, cucumbers. That was my first job, selling cucumbers out of a wagon. I was 5. I went around from door to door. My dad gave me cucumbers from the garden, and I went to the neighbors' houses and sold them for 10 cents each. Zucchini are gross. Cucumbers are decent. Just kidding. They're good. I like them now. All right, let's get back to focus here. So let's see if you can do this. All right, here's a question for you to try. Okay, I'm going to push pause for 1 minute. We'll see how far you get. Okay, another growth, and we have 8%. So this is going to be an original value of 1,200. So we have 1,200 times 1.08. Don't put 1.8 because that would be how many percent? How many percent? 80%. So 1.08 is 8% to the t, and this again is a function respect to time. We got 1,200 times 1.08 to the t. We want to know what's the value in 2016. So you have to do some thinking. You can't just put 2016 in for t, can you? Because what does t represent? T equals number of years after 2010, right? If you really are specific about it, because this formula was written in 2010, and so t is the number of years after that date. So in this case, if it's 2016, that means t equals 6. So then you put 6 in there and you evaluate. And does anybody have that value for me? F of 6. 1,904. Can anybody second that? Okay, so it's probably good. Now a little follow-up question. When will the sculpture be worth $5,000? So now we have to set that equal to 5,000. And we're going to have to use a log to solve for the exponent t. Excuse me, 1,200 original amount times 1.08 to the t. Okay, so this is what we did last unit. Divide both sides by 1,200. And those cancel out over there, so now we have, I'm just going to leave it as a fraction. I'm not going to take any time to reduce it or anything because I'm using a calculator. So 5,000 1/1200ths equals 1.08 to the t. So now I rewrite that as a log. That's going to be the log of 5,000 1/1200ths. Base 1.08 equals the time in years. And remember, if you have, some of you don't have a fancy calculator where you can change the base, so you might have to do this as the log of 500 or 5,000 1/1200ths divided by the log of 1.08 and use common logs for both. And that's going to equal your t as well, which Aaron was what? About 18.5 years. Anyone have any questions, thoughts on that? Okay. So the next is talking about decay. Decay is going to happen, or when decay happens, when we're talking about decay, we're going to subtract the rate from 1. So if something decays 5%, how much of it do we have left after it loses 5%? 95%, right? What if it decays 20%? How much do you have left? 80%. So if you want to try to find, like earlier when we talked about, if we're trying to add 20%, you multiply by 1.2. If you're trying to subtract 20%, then you want to multiply by 0.8. So you subtract it from 1. Yeah, because 1 is 100% as a decimal, right? Okay, so everything's the same except for we're subtracting the rates. So now if we have a population in a town that's decreasing by 3% per year, then I'm going to take, ooh, that's like what Ash would write with. Sorry, sorry, okay, now I'll stop with the whole green pen on the yellow thing that I couldn't read. So anyway, if it's decreasing by 3%, then we're going to have 0.97 to the t power. And the initial amount in this case was 1,700 people. So 1,700 times 0.97 to the t. Started in 2010. We want to know for 2022, so that was how many years? 12. So we're going to find f of 12, which is equal to this. Use my TI-85, my 23-year-old TI-85. I was just saying we used to be required to buy these calculators for high school. So like when I was a young lad, my parents or somebody bought me this calculator for probably 80 bucks or whatever. And it's kind of expensive. But it's a good idea to have your own, but we don't make you buy your own. But anyway, what are we doing? Is this people? So if it's people, should we round up or down, you think? I'd probably round down even if it was like 0.8 of a person, because it doesn't make sense to have 0.8 of a person. So you really only have one less. So this could go either way. You could argue, I guess, but I'm going to round down. 1,179 people. So what was different? You have to subtract the rate from 1 because it's decay. All right, another question with the follow-up. Same thing. So probably getting a little repetitive here. I'll give you a head start and then I'll put the answer up. Okay, let's see what you came up with here. So we have a local stream fish, declining fish population 4% per year. So that is going to be a 48,000 initial amount, right? And it's declining, so we have a 1 minus 0.04 or a 0.96 rate of decline or decay, whatever you want to say, to the t power. All right, same type of problem. Now you'd solve that. You put in 7 years for t, and what do you get? 36,000? 69.5. And it's fish, so I'd probably just say 69. Fish! When will the population of the stream reach 5,000? Oh, how many years until we only have 5,000 fish left? All right, well, this is going to be an equation that will involve using logs. 5,000 equals 48,000 times 0.96 to the, and I'm trying to solve for t this time. Right? 48,000, was that the right? Yep. So now, get the t by itself. I'm going to divide both sides by 48,000. And then I'm going to rewrite it as a log. So now I'm going to have the log of 48,000. Sorry, just kidding. 5,000 over 48,000. With a base of what? 0.96. And that will equal the time in years it takes. I think it's like 55 or something, if I remember right. 55 point, about 55 years. If you're reporting for the newspaper and you're going to use this model to predict, you probably wouldn't say 55.4 years. You'd probably say in about 55 years, it'll be down to 5,000 fish. All right, and the last thing we'll talk about is half-life. Half-life is a very common concept used. Probably done some in chemistry, maybe a little carbon-14, a little carbon dating. So here we're going to talk about the half-life of something I've never heard of. It's, well, here's the formula first of all. Half-life is just a decay formula, but we have the rate of decay is half, 0.5, right? And the time frame in which those things decay is based on the half-life of whatever you're talking about. So instead of just to the t power, we have to the t divided by h power, because it's not like it goes in half every year. It might go in half every 5 years or something. So you have to consider how many years it's going to take before it actually chops in half. Makes more sense when you give an example. So if we look at an example of this, how do you think you say this? I'm going to say astatine. I don't know. Never heard of it. So astatine has a half-life of 2 seconds. So after 2 seconds, there's half left. It's like gone like really quick. So find the amount left of a 500-gram sample of astatine after 12 seconds. Okay. So let's just take a time out here and think about this. How many times is it going to chop in half? If it has a half-life of 2 seconds And we want to know how much is going to be left after 12 seconds. 6 times, right? So that's why you just don't take it to the 12th power. You take it to the 12 over 2 power, because it's going to chop in half 6 times, not 12, because it has a half-life of 2 years. So that's why we have this like 1 over h or t over h part. So it makes a little more sense when you have actual values in there. So what we have here is we have a 500 grams of this stuff, and it's going to be reduced by 50% after 2 years. Well, if I want to know for 6 years, then that's going to be 6 over 2, so it's going to be halved 3 times. So you take half and you're going to get 250, and then you take half of 250 and you're going to get whatever, and you're going to, so let's take this to the power and see what we get. Oh, yeah, sorry. Thank you. I screwed up there. I know the answer needed to be 6, and then I put 6 in. 12 over 2. Yeah, my bad. So for 12 seconds, it's going to be chopped in half 6 times. Okay, so put that in your calculator. 500 times 1/2 to the 6th power. What do you get? $7.81. So 7.81 grams left. Okay. All right, wrapping this up. We have one more example, and then the last one is a little different, little twist we haven't seen yet. What about after 1 minute of astatine with a half-life of 2? Ooh, scary. 1 minute. How many seconds is that? 60. All right, don't fall for the old different units trick. Okay, you gotta have seconds to seconds here, right? So that's going to half 30 times. Well, there's not going to be that much left then. 500 times 0.5 to the 60 halves or 30 power. That's what f of 60 is. So after 60 seconds, we basically have nothing, right? We basically have nothing, but we're never going to have nothing. That's why we have an asymptote we talked about yesterday as y equals 0. It's never going to equal nothing, but it'll be basically nothing. So in this case, we have 0.00, how many zeros is that? 1, 2, 3, 4, 6 zeros, and then 466. So it's a really, really small number. You might see this number, I'll talk about this since it comes up. You might see this on your calculator as 4.66 e to the negative 7. The e is the scientific notation on the calculator, so that's the same as 4.66 times 10 to the negative 7th. So 2 other ways that you might run into that number in scientific notation. Whew, all right. The very last example, it says, when will this stuff reach only 1 gram? So we maybe want to know what year will it have only 1 gram left? Well, we're going to have to use a log. We say 1 equals 500 times 0.5 to the, and now this is where the different part comes in, t over 2, or 1/2 t, right? Because you got to take the t and divide by 2. And divided by 2 is the same as timesing by half. So now when I do the log and I do all that stuff, I'm going to have it equal to 1/2 t. So divide both sides by 500. Rewrite it as a log. You're going to end up with the log of, well, I guess I'm kind of skipping a step. Does that bug anyone? Well, I'm too bad. I go back. I'm not going to do it now. So we have 1 over 500 is equal to 0.5 to the 1/2 t. Now I rewrite it as a log. So if I rewrite that as a log, that's going to be the log of 1 over 500. The base is 0.5 or 1/2, and that equals 1/2 t. So to get rid of 1/2 t, because I want it to know what t is, I'm going to multiply both sides by 2. Multiplying both sides by 2 is going to get rid of the 1/2 t, so I'm going to have left just t. So t is equal to 2 times the log of 1 over 500 base 0.5. And you might have to use a change of base formula if you don't have a fancy calculator on that. Like I don't have a fancy calculator on mine. So calculate that out. What do you get? Log of 1 over 500 divided by log of 1/2 times 2. I got like 17.9, and that's what? Seconds? So after that calculation down there, I got 17.9 seconds. Sex. I just said sex on the tape. That's funny. I meant seconds, like SECS. Jeez, you guys. And the tape, like it's actually taping on tape. Yeah. All right. These are great outtakes for anyone that might be making a compilation someday. All right, that's a wrap. Anything else before we go? All right.